Mixing ratio. We're looking for a way of characterising how much moisture is in the atmosphere. So consider air containing both dry air and a quantity of water vapour occupying the same region in space, that is the same volume. Let's define then the mixing ratio, R, which is the density of water vapour over the density of dry air. But because they occupy the same volume, and density is mass over volume, the mixing ratio R is equal to the mass of water vapour over the mass of dry air. R is a dimensionless number, and therefore the mass of water vapour and the mass of dry air are both measured in kilograms per kilogram. But because the mass of water vapour is typically much less than the mass of dry air, the mixing ratio is often expressed in units of grams per kilogram, and that's the way it's plotted on a skew T log P aerological diagram, or F160. So let's define the mixing ratio as the actual amount of vapour that is in an air parcel at a given temperature T. And so R is the mass of vapour in grams over the mass of dry air in kilograms. Shown on the right is a skew T log P aerological diagram with the isobars running horizontally, the isotherms at a skewed angle, the sloping dry adibats, and then the skewed mixing ratio isopleths, and shown there is 0.1, 5 and 40 grams per kilogram of water vapour. We can also define the saturated mixing ratio RS as the maximum amount of vapour that can be in an air parcel at a given temperature T. So for a given temperature T, we'll have a given evaporation rate, and if there's sufficient liquid water available to evaporate, the air eventually becomes saturated with amount of water vapour in grams over the mass of dry air in kilograms being equal to RS. There's a bit of maths on this slide, so if you need to stop the video and just find your way through the maths, then do that. The mixing ratio R is the density of vapour on the density of dry air, as we've seen, and if you multiply the equation top and bottom by temperature, you don't change anything, but what you can do is use the ideal gas equations for dry air and vapour to replace the terms rho T. The pressure due to the dry air, PD, is equal to rho D, RD by T, and the vapour pressure E is equal to rho V, RV by T. Substitute for rho T for both expressions, and then flip the two fractions that you get on the numerator and the denominator, and you end up with the expression R is equal to E on PD, RD on RV. Now we can define a ratio between the gas constants. Epsilon is equal to RD on RV, and because the equations for the specific gas constants involves the universal gas constant divided through by the molecular weight of the particular constituent, epsilon may be written as the molecular weight of vapour over the molecular weight of dry air, which is about 0.622. We can also write the total pressure as the sum of the partial pressures, that is the pressures due to the dry air and the water vapour. P is equal to PD plus E. So we can substitute RD on RV for epsilon, and we can substitute PD in the denominator of the equation for P minus E. And so the mixing ratio might be written as epsilon E on P minus E. You can then rearrange that equation and re-express that in terms of the vapour pressure. So E is equal to R on R plus epsilon by P. And I'll leave that as an exercise for you to do to show that that's the case. We can also define a saturation mixing ratio, and it's written in the same way as we did for the mixing ratio. RS is equal to epsilon ES on P minus ES, and P minus ES is PD. On the F160, for a trace with a given pressure, temperature and dew point temperature, the point where the isopleths of mixing ratio cross the dew point profile gives you the mixing ratio for that given pressure, and the point where the isopleths of mixing ratio cross the temperature line, that gives you the saturation mixing ratio.